Today we're reading out loud section 420, Isotropic Vector Matrix. To prepare for this section, it helps to have in mind the cuboctahedron. That's the name from classical geometry. We're going to call it the vector equilibrium. If you take a center point, here's a model. You can see the blue lines as a center dot, and then if you draw a vector in all directions, you end up with an equiradiating set of 12 vectors, and the outer surface would form a cuboctahedron. You can see the blue vectors. And then we're going to extend that to the idea of a truss, which is drawn here. You can see one vector equilibrium in there, or one cuboctahedron, and then it's extended outward. It's a little harder to see, so it helps to have a tetrahedron, double in size, two struts making up each length, and then you get an octahedron in the middle, and the cuboctahedron. And what can really help is to have a way of seeing one emanating from the other, and so that's what this model shows. Here's the cuboctahedron, and then there's a tetrahedron emanating here, and that's what we're going to be covering. And we're going to call all of this the isotropic vector matrix. Section 1. When the centers of equiradius spheres in closest packing are joined by most economical lines, i.e. by geodesic vectorial lines, an isotropic vector matrix is disclosed. Isotropic meaning everywhere the same, isotropic vector meaning everywhere the same energy conditions. This matrix constitutes an array of equilateral triangles that corresponds with the comprehensive coordination of nature's most economical, most comfortable structural interrelationships, employing 60-degree association and dissociation. Remove the spheres and leave the vectors, and you have the octahedron-tetrahedron complex, the octet truss, the isotropic vector matrix. And that's what I showed you in our little preparation. Here are spheres drawn, and then if you just take the centers of the spheres and remove the spheres, then you have the nodes or the vertices. Here he has rendered it as an octet truss, which is kind of one flat layer extending forever. Here's one unit of it. There's an octahedron with the tetrahedron associated. And in this drawing, you don't see the spheres at all. Here you can see again the spheres. You can use the spheres and close pack them to get the vector equilibrium or isotropic vector matrix. Vector equilibrium, we call it when we're thinking of the fact that all of the vectors add up to 0. It's an equilibrium. And isotropic vector matrix, we call it when we extend it to infinity. Section 2. The isotropic vector matrix is 4-dimensional and 60-degree coordinated. This is 4-dimensional in Fuller's use of the word of the dimensional and not the classic orthogonal dimensions of geometry. It provides an omnirational accounting system that, if arbitrarily accounted on a 3-dimensional 90-degree basis, becomes inherently irrational. The isotropic vector matrix demonstrates the ability of the symmetrically and asymmetrically terminaled high-frequency energy vectors to accommodate the structuring of any shape. So here it's omnirational and then asymmetric or symmetric. The tetrahedron here as a volume of 1, then the octahedron will have a rational, an integer volume of 4, and all of these are the rational or integer relationships, or by ratio rather than irrational. And if you measure in Cartesian coordinates, you will have to use irrational numbers, meaning you'll have to use 3-point dot in all kinds of decimal places, because what you're trying to do is express it with a polynomial. Chop off certain pieces, you will get A modules and B modules, which are asymmetric. They're not perfectly symmetric, but they still form part of this rational accounting. 3. Our extension of the Avogadro hypothesis generalizes that all energy conditions are the same. Inasmuch as vectors describe energy conditions, this would mean a volumetric aggregation of vectors in a structural complex in which all of the interacting vectors would have to be of the same length and all of their intersecting angles would have to be the same. This state of omnisameness of vectors stipulates the isotropic, meaning everywhere the same. This prescribes an everywhere state of equilibrium. Avogadro is important to Fuller because Avogadro stated that all gases under identical conditions of heat and pressure will always disclose the same number of molecules per given volume. Here's a short video that explains it well.
All gases have the same number of molecules per cubic centimeter, no matter the size of the molecule. That's because they are absolutely tiny compared to the distance between them. Even if your molecules are multiple times bigger, they don't really take up more space. So unless you are dealing with extreme pressure or temperature, all gases have the same number of molecules per cubic centimeter.
4. Equilibrium. 0.041. Nature is said to abhor an equilibrium as much as she abhors a perfect vacuum or a perfect anything. Heisenberg's indeterminism and quasi-precision mechanics recognition of inherent inaccuracy of observation or articulation seems to suggest that the asymmetric deviations and aberrations relative to equilibrium are inherent in the imperfection of a limited life of humans with a tightly limited range of perceptible differentiation of details of its experience. Heisenberg, of course, has the uncertainty principle where you can't know momentum and location at the same time, and Fuller is generalizing this to a inability to measure things perfectly, a built-in inaccuracy into nature. Nature demonstrates her abhorrence of equilibrium when an airplane in flight slows to a speed that reduces the airfoil lift and brings the airplane's horizontal flight forces into equilibrium with Earth gravity's vertically earthward pull. The plane is said then to stall, at which moment the plane's indeterminate direction makes it unmanageable because the rudder and elevator surfaces lack enough passing air to provide steerability, and the plane goes swiftly through equilibrium and into an earthward spinning plunge. To illustrate lack of equilibrium, Fuller illustrates it with an airplane not managing to maintain speed and going into a stall. Despite the untenability of equilibrium, it seemed to me that we could approach or employ it referentially as we employed a crooked line, the deliberately non-straight line, that approaches but never reaches the perfect or exact. You can examine the non-straight line. It's a way of making more concrete the fact that, of course, a line can't be perfectly straight in the natural world. It will also always waver a bit. A comprehensive energy system could employ the positive and negative pulsations and intertransformative tendencies of equilibrium. The vector equilibrium became the logical model of such omnidimensional, omni-experience accommodation studies. Because we have learned that scientists have experimental evidence only of waves and wavilinearity and no evidence of straight lines, it became evident that the radial and circumferential vectors of the vector equilibrium must be wavilinear, which meant that as coil springs, when compressioned, will lessen in length and when tensed will increase in length. Ergo, the explosive disintegrative radial forces of universe would compress and lessen in outward disintegrative length and would be well inside the closed back on itself hexagonally tensed embracing vectors, indicating a higher effectiveness of tensile integrity of universe over any locally disintegrative forces. The comprehensive vector equilibrium system would also have to recognize all the topological interpatterning characteristics and components. Also, as a quasi-equilibrious system, all of its structural component vectors would have to be approximately the same length. Therefore, all the interangulation would have to be in aberration increments relative to 60 degrees as the equilibrious norm. The springs and closing back in on itself can be seen in this illustration. Down here, when you look at the graphs of the cuboctahedron, which is an essential part of the isotropic vector matrix. You have octahedral, tetrahedral, but here in the centrosymmetric, this yellow ring is a hexagon, then this green ring is a hexagon, this blue ring is a hexagon, and then the red, flush centered to the viewer, is a perfect hexagon. These hexagons, Fuller's pointing out, can be seen as binding tension elements, and then they're holding in tension the internal compression struts. So the springs inside would be compressed and the rings would be tensed. 5. The closest packing of spheres model coincides with the observed world's atomic packing of like atoms with their own counterparts. Fuller's suggesting that the atoms in the world will arrange themselves the way spheres arrange themselves in close packing. Then when you close pack, you end up with 60-degree coordination, you end up with the vector equilibrium, and in turn, the isotropic vector matrix. Section 6. We find that the space compartmentation formed by the vectors connecting the sphere centers always consists only of tetrahedra and octahedra. The spheres in closest packing coincide with the Eulerian vertices. The vectors between the sphere centers are the Eulerian edges, and the triangles so formed are the faces. Faces is in quotes because the faces don't actually exist. Fuller will prefer to call them windows because they're open space. And that's Euler, meaning traditional geometry. 7. All of the polygons formed by the interacting vectors of the isotropic vector matrix consist entirely of equilateral triangles and squares. The squares occur as equatorial cross-sections of the octahedra. The triangles occur as the external facets of both the tetrahedra and the octahedra. And here you can see that with a bit of effort. There's that square right in the middle. See that square there, face on? The square gets formed as a result of the triangular coordination around it, and it forms the center of the octahedron. There's an octahedron right in the middle there, and it has an equatorial square. 8. All the polygons are reducible to triangles and are not further reducible. All polyhedra are reducible to triangulation, i.e. to trusses, and are not further reducible. Infinite polyhedra are infinitely faceted by basic trusses. Join us for more Reading Out Loud, Synergetics, which is a project of the Tensegrity Wiki. Visit us at tensegritywiki.com.